In this video, we'll discuss noise-based fields, which provide various types of pseudo-random properties. This section builds on concepts introduced earlier in the series, so I recommend at least watching the concept section before this one. We'll be using version 0.27, but most of what we'll cover here is also available in earlier versions. Before we discuss the noise fields, we're going to need to set up some renderers that we can visualize them. We're going to run through this part quickly since this isn't the main focus of the video. Open the palette with the Alt-R shortcut and create a render 2D. And then create a null top connected to the first output so you can see the result. I'm going to set the resolution here to fit it in the side panel, but you do not need to do that. Then we're going to set the zoom to 0.5 and then create a null dat and connect that to the input on the renderer. And this is where we're going to connect our fields for 2D visualization. Open the palette again with Alt-R and create a RayMarch render 3D. And create a null top connected to the output. Again, I'm going to set the resolution here to fit it in the side panel. With the renderer selected, use the Alt-Shift-R shortcut to open RayTK's Editor Tools menu and choose Add Look At Camera. On the camera, we're going to set the FOV angle to 70 and the position to 445. Create a box SDF and connect it to the first input on the renderer. We're going to set the uniform scale down to 0.2. Create a modulo 3D. And we're going to insert that between the box SDF and the renderer. Change the size for all three axes down to 0.5. And then for the limit type, we're going to set that to both. And we're going to increase the limit start, all three parts, up to -4, -4, -4. And then for the limit stop, we're going to do the reverse and decrease all of those down to 444. In an earlier release of Touch Designer, version 2022.29850, there is a bug that will cause Touch Designer to crash if you do this next step. So I recommend updating to 2022.31030 or later. Open the palette again and create an assign color operator. We're going to insert our assign color between the modulo 3D and the renderer. Then we're going to create a null dat and connect it to the second input on the assign color. And this is where we're going to connect our 3D fields for visualization. So we've just created two different ways to visualize fields. The first one is 2D, and it's really simple since we can just directly connect a field to the renderer. For 3D, we're creating a grid of small boxes, and then we're using a field to assign a color to the surfaces, and then we're rendering it using RayMarching with a camera angle that gives us a view of all three axes. We'll start with noiseField. Open the palette again with Alt-R and create a noiseField operator. And connect it to the null dat for our 2D visualizer. And I'm going to switch back to show that output. On the noise field, on this coordinate type parameter, if the auto option is available, then just use that. If it isn't, like in this version here, we're going to change it to 2D. The noise field operator is similar to a noise top or the noise component from the Touch Designer palette. In fact, it shares some code with the palette component. It uses one of a number of different techniques to produce pseudo-random values based on the coordinates that it's provided. By default, it's using the simplex 2D technique. The simplex part of the name is a type of noise algorithm, and the 2D part means that it does its calculations on 2D coordinates. Try changing the x and y parts of the translate and scale, and see how it moves the pattern and stretches it horizontally and vertically. Then try changing the translate for the z parameter, and see how that isn't making any noticeable change. And that's because this pattern is based on 2D coordinates, so any offset along the z-axis isn't going to have any impact. Change the noise type to simplex 3D. Even though we're using this field in a 2D context, since the renderer is 2D, we can still use noise types that do 3D calculations. It just sets the z-axis to 0 and uses the x and y axes. Now when we try changing the z translate, we're going to see that it changes the pattern, but not in a way that moves it either horizontally or vertically. This is essentially taking a 2D slice of a 3-dimensional pattern, and we're moving where that slice is forwards and backwards. Using z translation with a 3D pattern in a 2D context is a good way to make the pattern change without it either moving vertically or horizontally. We can even use noise patterns that are based on 4D calculations. So change the noise type to simplex 4D, and now we have this fourth translate and scale that we can use to shift the pattern. Changing either the z or the w in this case is going to produce kind of a similar result in that it will change the pattern without shifting it horizontally or vertically. Next, we can take a look at noise fields in 3 dimensions. Now I'm going to switch my output to show the 3D renderer, and then we're going to open the palette again and create another noise field. Again, if the coordinate type auto is available, just leave it on that. If not, make sure it's set to 3D. And we're going to connect this to our null dat for the 3D visualization. Try adjusting the translate x and y, and you'll see that you're moving that pattern along the x-axis and the y-axis there. But right now, the whole pattern stays the same along the z-axis, and that's because it is using a 2D calculation. You can change which axes it uses for that using this axis parameter. So right now it's set to z, meaning that those 2D axes are x and y. You can change it to y, and that way it will use the x and z axes and so on. But we're going to switch it back to z here. Change the noise type to simplex 3D, and now you can see how it is changing the pattern along all 3 axes. So you can use translate for x, y, or z, and you can stretch or shrink the pattern along each of those axes. Change the noise type to simplex 4D, and now we can use this fourth translate parameter and see how it shifts the pattern, but it isn't doing it along any of the axes that we can see. So it's not doing it along x, y, or z, it's just kind of shifting everything sort of in place. And this is similar to how we used a 3D offset when we're doing a 2D rendering. There are a number of different noise types that we can use in here that are mostly kind of similar to simplex. We've got curlN, a few different variations of that, another variation of simplex, and so on. We're going to go back to look at our 2D noise. So switching back to our 2D visualizer, going to look again at the noise field here. Change the noise type to cheap random lookup. This gives us a pattern that looks like static. Touch Designer has a built-in texture that has randomized data in it that's available to shaders, and this noise type just looks up values from that texture. The result is that it's very efficient, but since it's just reading from a pre-computed texture, if you scale out far enough, you'll see the pattern starting to repeat. It's worth noting that most types of noise patterns involve lots of calculations, so they can have a sizable impact on performance. So when you just want random values without having it be expensive on performance, cheap random lookup can work. Now change the noise type to Cellular 2D. Now change the noise type to Cellular 3D. This type uses a Voronoi pattern that looks sort of like how bubbles behave when they're pushed together. So if you can zoom out there, you can see that you've got a bunch of these little cells. In the center of each cell, it's going to be dark, and then as it gets closer to the boundaries between them, it's going to get lighter. You can also change the amplitude and the offset to change the range of values that it produces. All of the noise types that we've covered so far are just producing single values. That's why all of the output has been in grayscale. But some types of noise produce vectors with different values in each channel. Change the noise type to Cellular 3D Derivative. This mode is similar to the regular Cellular 3D noise, but it produces more data in different channels. In the top viewer, you can switch to Normalized Split to see each of those channels separately. So the red channel is the same as what the regular Cellular 3D type produces, but the green is a horizontal ramp from 0 to 1 within each cell, and then the blue channel is similar but vertical ramp, and then the alpha channel is a different value for each cell, so you can use this to differentiate between the cells. Similar to other types of noise in here, you can also use this kind of translate to shift the pattern along any of these axes. Next, we'll look at the curlNoiseField. Open the palette again and create a curlNoiseField, and connect this to our 2D visualizer. Again, if the coordinate type isn't set to auto, we're going to change it to 2D. And then we can just go back to our regular color view here. Curl noise is similar to Perlin noise, but it uses slopes to produce vector values that create curling patterns if it's applied to motion. It has similar parameters to noiseField, in that it's got translate along each of these axes, and then also along the z-axis, and then a scale to grow or shrink the pattern, and then amplitude to increase the range of values, or offset to shift all the values in one direction or the other. Switching back to our 3D visualizer, we can create another curlNoiseField and make sure this one is set to either auto or 3D, and then connect it up there. And you'll see that you get a pattern along all three of the axes. And if you increase the scale there, you can see how you can shift it along any of those axes. Next, we'll look at the waveletNoiseField. So switching back to our 2D visualizer, open the palette again with Alt-R and create a waveletNoiseField. And we're going to connect this to our 2D visualizer. And then again, either use the auto coordinate type if it's available, or 2D. Wavelet noise is an algorithm that was developed at Pixar. It combines multiple layers of transformed sine waves to create a complex pattern. To see how it works, we can reduce the number of iterations down to 1, and then scale our period down to 0.5 along all the axes. This pattern divides space into a grid, and then within each cell, it produces a circular pattern with a sine wave of values in some direction. You can use this phase parameter to shift each of those patterns. And see how it is basically just a repeating pattern within each one aimed in a different direction. If you switch on vorticity, the phase is also going to cause rotation in those patterns. Increase the iterations to 2, and then try adjusting the scale factor and see how it's basically taking 2 of those types of patterns and layering them on top of each other. So if your scale factor is really low or you have a low number of iterations, it can be kind of clear what the basis of this pattern is, but when it gets higher, the patterns start to interfere with each other and you get a more randomized look. And then you can increase the number of iterations to add even more layers of variation to that. Lastly, you may have noticed that these noise operators all have an input labeled coordinate field. By default, when an operator asks one of these fields for a result for some position in space, it will use that position as the basis for the noise pattern. But we can also use another field to produce those coordinates. So switch back to our noise field, and then we're going to go just back to Simplex 3D. Open the palette again with Alt-R and create a wave field. And then connect this to the input on the noise field, the coordinate field input. Try increasing the period on that wave to spread out the pattern, and you can use the phase to shift the whole thing. So notice how the pattern repeats, and this is because the wave that's being used as the coordinates repeats. So anywhere that that wave produces a value of 1, as far as the noise field is concerned, those spots are the same, so they're going to produce the same result. On the noise field, try changing the xTranslate parameter, and you'll see how it shifts the pattern, but it's doing it in a way that repeats because it's still based on that wave as the coordinates. If you change the yTranslate, it's going to change the pattern, but not along the axis that's being used by the wave. Try changing the wave field's axis to y. So now the wave that we're using for that coordinate is going along the y-axis. On the noise field, try changing the xTranslate, and you're still going to get it moving along wherever that wave is pointed. And the y-axis is going to do something similar to what it used to do. This is because even though the wave field is looking at its y-axis, it's producing a single number that just happens to be in a pattern along that y-axis and passing that over to the noise field, which uses it as its x-coordinate, since it's only getting one number. We can also use fields that produce vectors to provide coordinates. So change the wave field's axis back to x. And open the palette again with Alt-R and create another wave field. And this one, we're going to change the axis to y. Then create a float to vector operator, and we're going to connect our two wave fields to it. Then we're going to keep the part source X on input 1. For the part source Y, we're going to change it to input 2. And then for the other two parts, we're going to change those both to 0. And then we're going to connect this to the NoiseField's input. Try adjusting the parameters of the two waves, and you'll see how we've got two different waves that are, each one is controlling one of the axes. So combined, these two are producing an X and a Y value, and that's what the noise field is based on. If you adjust the translate on the noise field here, you can see that it's moving along one of those waves for that, and then if you're doing it along the y-axis, it moves along the other wave. This technique can be used to create randomized patterns that repeat or behave in predictable ways. And that's it for this section. You can try using different types of noise fields to drive parameters in your scene, like assigning colors, offsetting surfaces with the round operator, and so on. Stay tuned for the next video in the series. Check out my Patreon for access to scene files, exclusive tutorials, and more. And as always, thanks for watching, and make sure to like and subscribe.